Hey guys, it's Dr. Metis here, and I just want to do a quick little conversation with you about acids and bases and focus really on the conjugate pair issue of acids and bases. I wrote on here in the green, acids are H positive proton donor, bases are proton acceptors. And in a chemical reaction, you always have this before and after picture. And if an acid donates its proton, once it's done that, once it's donated proton, then it's in a position typically to accept proton. So what acids do, once they are done donating, they become bases. Once bases have accepted proton, they become acids. And it's this back and forth flow that is between reactant and product. As an acid becomes a base becomes an acid, that creates your conjugate pair. And so doing, before we get into a little bit further, you have to be able to identify things. And the easiest way to identify any of this is that acids have H positive, bases don't. And to hook first year students up, typically we write the H up front. You have HCl, HF, okay? And you recognize that as acid because it has H up front. But like F1 negative, you recognize as a base because it doesn't have H up front, okay? Even something like ammonia, NH3, it has H's, but they're not up front. And so if you want anything else, you just say, hey, that's not an acid because it has H up front. I mean, but N does have H's, but they're not donatable. And sometimes for first year students, it's kind of hard to see whether the H is donatable or not. So we put it up front. Like for acetic acid, which really looks like this, CH, H, H, C double bond O, OH. This H is your donatable H. These guys on these nonpolar covalent bonds, not so donatable. They're not acidic at all. But again, it's a lot for the first year student to get, and we basically don't want you to get lost in the muck. We just put the H up front. We'll say it's H, C2H3, O2, and we say, hey, that's the H. I don't want you to focus on H's on O's. Just for right now, just throw it up front to hook you up a little bit. Once you get used to seeing where those H's are that are donatable, a lot of it makes sense. So if we can scroll over, if I can actually move my bar, and we look, I have some problems set up. We can identify conjugate acid-base pairs. They're kind of easy to do. I mean, here's the long, laborious way that a lot of teachers will do. Okay, they'll say, hey, if you look at this, you have nitric acid right here, and then you have potassium chloride, and it looks like the nitric acid has donated its H positive because it no longer has it. And so if it donated H positive, that's the acid. Chloride has accepted the H positive, so that's the base. If you were to reverse these reactions, for HCl to combine with potassium nitrate to reform those reactants, then HCl would have to donate H positive, and that means it's an acid. And NO3 would have to accept H positive, that means it would act as a base. Because then you have to create your acid-base pairs. You have an acid teaming up with a base, that must be a pair. Base teaming up with the acid, that must be a pair. To do all that is really cumbersome, and I really don't like it. It's a good conversation, but on a test, you have to work about, getting through everything. So you don't, I think it's easier to look at this and say, hey, what are my things that are alike? This is my dividing line. I got NO3 here, nitrate. I have a nitrate over here. I have Cl here, Cl there. Those are your pairs because it's the anion of the pair that makes the acid or the base. If it has an H with it, it's going to be an acid. No H, it's going to be a base. Realistically, it's the one with the more H's that's the acid. And if you look at this then, HNO3, that would be your acid because it has more H's, okay? And this would be your base with that intake. So you have your acid, you have your base, and it's a conjugate pair. Which one's the conjugate? Just depends whatever you're talking about. HNO3 is an acid, so this would be the conjugate base. But look at it another way, that's the base, so this must be the conjugate acid. Most teachers like it if you label the product as the conjugate. Me in my classroom don't really care. I just want you to be able to find the pair. KCl and HCl, H is more H's, so this is your acid. this is your base. And they create what we call a conjugate base pair. It's a bit not theoretically, it's a reaction I can write, but you're not really going to see that reaction very much. B and C represent, I think, truer reactions. But if you look at B, find the guys that are alike. Which are your pairs? Okay. Well, VO3, the vanadate, there's another one that looks a lot like it. They're only differing in their H's, okay, and the charge. And if you look at the ClO2, chlorite with the chlorite, within that pair, you have an acid and a base. The one with the most H's is your acid. So HClO2 must be an acid, ClO2 negative, there's your base. As far as the vanadate goes, hey, that has 2, that's your acid, that's your base. So we're color coding it for the conjugate acid base pair. And if you look on each side of the reaction, we have an acid and a base reacting, acid and a base being formed. The base is becoming an acid, the acid is becoming a base. So we know we're right. And letter C, we got the bicarbonate, CO3, hooking up with CO3. There's a pair. Cl with Cl. Within the pairs, which has the most H's, carbonic acid is your acid, has 2 H's. The bicarbonate only has 1, it's the base. Okay, for HCl, that's your acid, that's your base. For you college level students, your advanced placement type students, if you're taking chemistry in a second year, you're going to learn that things like this aren't really bases. They are in this definition, how we're identifying them, but later on you'll learn that conjugate bases of strong acids are a little bit different. But for right now, first year chemistry students just trying to find conjugate acid base pairs, that's definitely a good conjugate acid base pair. Ready? Applying that, what you're often asked to do then is identify things as acids or bases and say what would they make. And this is going to get a little tricky, but straightforward at the beginning. HBrO3 is definitely going to be an acid because it has an H up front. Okay? Acids, whoops, showing the phone right there. Acids lose H positive. So because we're labeling this as an acid, he is going to lose H positive. And so BrO3 would be what would remain if we lose an H, lose the H. But we've also lost a positive. We've lost the whole proton. So a neutral compound becomes a negative when it loses a positive. Kind of cruise through a couple of these. The one next is sulfite. Sulfite is a 2 negative. It looks like it can't be an acid because there's no H up front. It can definitely be a base. And I should add, if a base is going to accept proton, it needs some way to attract the proton. Earlier, I said ammonia over here is definitely a base because it has a lone pair of electrons on the end. It has this lone pair of electrons that can attract an H positive, okay, and form a bond to it. Well, so over here, we label that as a base, and we say that's going to accept H positive. So we put it's H and H3 positive, or merely just it's NH4, 1 positive. Ammonia is probably the only time with the nitrogen that you're going to combine your H's. Look at letter B again. It's negative. That means it can really attract an H positive. That's one way you know it's a base, other than the obvious it ain't got no H's. So add 1 H to it, and you have HSO3. A 2 negative with that positive, 2 negatives and a positive, leave only 1 negative. So it's HSO3, 1 negative. Okay. Skipping along because I think I'm getting long in the tooth. Well, maybe you can see another one. HCl. Okay. HCl is definitely an acid, has an H up front. Okay. So if you lose H positive, it's a lot like letter A up here. Lose an H, we have Cl is the only thing that remains. It was neutral, lost a positive to 1 negative. It's kind of like on a number line. 1, 2, minus 1, minus 2. If you're here and you lose a positive, you go backwards. For the SO3 2 negative down in letter B, we were right here. We gained a positive, went to -1. The other way to look at it is we had like 2 negatives and a positive, well, these eliminate each other. We only have one negative left. Really just depends upon how you want to see it. For the carbonate, that's also going to be a base. It looks a lot like the SO3, it's CO3. As it's a base, it's going to accept proton, gain one H positive, slap an H out front, and deal with the charge. 2 negative and positive is a 1 negative. I think most students tend to screw up the charge because in their head, they say they're gaining H. You can't be the texting generation and just shorten everything. You don't want to gain H, you want to gain H positive and constantly remind yourself that you're gaining in the positive as well as the H. Okay, it's really common. I see on my students on their tests that they're going to mess it up. They add the H in, but they totally forget about the charge. And I swear it's because you're saying I'm adding H. Don't add H positive. Our last little tidbit is this groovy little guy down below in letter F. And letter F, you have the H up front, so you think it could be an acid, and so you slap down. If it's an acid, it's losing H positive. So I'm going to have C2O3, and it was 1 negative, and I lost a positive, so it's going to become even more negative and be a 2 negative. And at this point, or perhaps earlier, you noticed he was negative, and things that were negative were bases. So you hesitate and go, oh crap, maybe I'm wrong. Maybe it's a base. I should add an H positive, in which case I have H2, C2O3, and a negative and a positive make neutral, so he's neutral. Is that what's going on? And you would say, yeah, that's perfect, man. Both are going on. Okay? He has an H that's donatable, so he could act as an acid. He's negative, so he could attract an H. So yeah, that species could act as a base. Okay? These things are called amphoteric or amphiprotic. The words I'm looking at saying are amphoteric and amphiprotic. They mean the same thing pretty much. Whichever one floats your boat. They can do either thing. They can act as an acid or act as a base. It just depends what other species it's with. Who's it reacting with? If it's reacting with a base, it's going to act as an acid. If it's reacting with an acid, acid will react as a base. We saw these amphoteric things up here. Amphoteric, but we saw he's acting as a base. H up front, negative, amphoteric, said he was going to be an acid. H up front, negative, amphoteric. Okay, said he was an acid. And last one, just to beat it, bicarbonate is a base. He's really amphoteric. He could have acted as an acid, donated the H positive, but it's with who they are with. So I hope this clears up this whole conjugate acid-base pair thing, either in reactions or individually. If they're in a reaction, they can't be amphoteric because you know how they're behaving. So if they're all by their little lonesome, like they were down here, if they're all by their lonesome, then you don't know how they're going to behave. So you gotta give me both. So really hope this helps. Have a good time. I hope you like it, and I'll talk to you later.